So in chapter number 15, we are going to be covering routing concepts. All right. In fact, for the whole day, we're going to be covering routing concepts. We're going to be talking about routing in general, and then we'll be talking about doing things like static routing, default routing. We'll be taking a look at also RIP, OSPF, EIGRP. So very, very busy day today with routing. All right. We know that routing occurs at layer 3 of the OSI model. And we know that the router is responsible for ensuring that traffic flows from one interface to the other. We also know that routers make their routing decisions based on destination IP address in the packet header. So as data flows from this PC, it's going to send its information to the default gateway. That router is then going to use its routing table, and in this particular case, a connected route to then forward that traffic on to the destination. We also know that a router does something else with this information. The router strips off layer 2 and then re-adds layer 2 as the information leaves the interface. So in this particular case, the source MAC address is the PC. The destination MAC address is the Ethernet MAC address on that interface. But that information gets stripped off. So as the data leaves, the source MAC address is the router interface. The destination MAC address is the PC on the other side of the network. Okay? Routers have the same kind of memory as a switch does. It has RAM, which is used to store our store all of our dynamically created tables, like our routing table, our ARP cache, and so on. It also is where we run our working iOS, our operating system. Essentially, everything that's happening dynamically in this platform runs in RAM. In addition, we also have our running config that is running in RAM. Flash is where we're going to store things like our operating system. Typically, it's the binary format of our operating system, which is just a compressed format of the iOS, or multiple iOSs if we have enough space, as well as firmware files and any other files that the system needs to use to perform functions and operations on the platform. ROM is our bootstrap. The bootstrap stores a limited version of iOS and stores our, it stores our information necessary for doing a platform recovery. It stores things like boot instructions, other things that are necessary for the platform to function. You can kind of think of ROM as a bootstrap or a BIOS, but it's a little bit more involved than just simply having some hardware-based instructions for booting up. We can actually manipulate those instructions and facilitate different booting methods on that platform. The NVRAM, this is where our startup config is stored. Our startup configuration file is stored here. They say it's the backup configuration file on the slide here, but in reality, it's our primary configuration file. When the device boots up, that startup config becomes the running config. Okay? And that goes into my working memory. We also know that routers interconnect networks. We're in a meeting center here. Each one of these meetings is a subnet or a room that people are participating in. The hallway that interconnects the rooms is kind of like the router. If you want to get from one room to another, you go out that interface or out that door, and you go into another interface or another door to get into a different room. So we are doing the same thing with our routers as well. We're allowing connectivity with our routers by having multiple interfaces connected to multiple networks, multiple destinations. Okay? Every single one of those interfaces is participating in a different subnet. Every single one of those interfaces is participating in a different subnet. That's what we were talking about the other day when we were talking about this subnetting concept. The subnetting concept is simple, right? You have to create a different subnet for every router interface. So this router down here has 5 different networks it's attached to, which means it's going to be participating potentially in 5 different subnets. This router here has 3 different networks it's attached to. This router here has 4 different networks it's attached to, and so on. So we know that routers, the goal of a router is to pass information from one network to another. Ultimately, with that goal being that we want to get the information to its final destination. But when it comes to routing, what is the primary function of a router from the perspective of a packet? The primary function of a router is simply to get that packet to the next host, the next router, or its final destination, if the destination happens to be connected to that router. In order to do this, routers have to choose the best path. If I go back to this diagram here, this router down here has multiple ways that it can reach different destinations. We have that for the purpose of load sharing, we have that for the purpose of redundancy, network resiliency, and so on. So routers have to choose the best path in order to reach a particular destination. The routing table is the path that was chosen. Very, very important to understand. What goes in the routing table is the path that was chosen by the router. There are other databases that we're going to see later on. There are other databases that we're going to see later on that allow us to store information besides the best path. But ultimately, what goes into the routing table is the best path. Now, how does a router determine that best path? Well, it depends on the method of routing. It could be based on hop count. It could be based on bandwidth, delay, reliability, and load. It could be based on cost. It could be based on BGP path attributes. So different types of routing mechanisms use different methods to determine what the best path is. Now, once that path is chosen, it goes into the routing table. So the routing table is a repository for the routes that we're actually using. What happens if there's not a route in the routing table for a particular destination? What happens to the packet? If we don't have a route for a particular destination, unless we have a default route, we'll talk about that later, but a default route technically is still considered a route. Unless I don't have a route, unless I have a route, excuse me, the packet will get dropped, right? So it says here, forwards the packets towards the destination. It goes out of a particular interface. In the case of a routing table, that interface is called the exit interface. The interface that the packet leaves from on the router is called the exit interface. Encapsulates the packet and forwards it towards a destination. What do they mean by it encapsulates the packet and forwards it towards the destination? They mean that once the router, or once the packet is leaving the router, it has to be, what? Reframed. Whether it's going over a PPP link, an HTLC link, an Ethernet link, that data has to be reframed and sent out the interface. Now, there are essentially two different ways that a router will route. It'll either use static routes or some dynamic routing protocol process. And we're going to learn all about different dynamic routing protocol processes as we move forward through the rest of today. Routers don't do anything unless they're told to do something, period. All right? Routers do not do anything unless they're told to do something. and we can tell the router, we can instruct the router to route based on a static entry that we put into the database, or we can instruct the router to route based on some sort of dynamic routing protocol process. So there's an algorithm that we use to decide that. Routers choose the best path based on something called a metric. Metric refers to a generic term that describes how routers select a path to their destination. The path with the lowest metric, based on whatever criteria that we're matching, is the path that gets chosen ultimately. All right? Now, if you guys remember this particular topology here, this is the topology that we were working with previously when we were talking about setting up our routers initially. Well, we are going to be adding IPv6 to this topology this morning. So I want everybody to go ahead and open up that topology that you had previously created. And we are going to be adding IPv6. All right? Let me know when you have that file open so we can continue with our lecture and our discussion, because it's important that we follow along, right? We're going to be, like I said, adding IPv6 to this network, IPv6 to this network, and this network, and this network, and this network. In addition, we'll also be adding IPv6 to our clients. All right? Now, the reason that we're doing this is because we want to make sure that you guys have a good understanding of not only how we do things in IPv4, but also how we do things in IPv6. Very important concept. All right? Excellent, Mike. You guys got your file open? Did you save it? Yes. Okay. All right. So the first thing I want to do before we start to go through this process here is I want to make sure that you guys, that we go ahead and verify that our IPv4 stuff is still there, and then we can go in and start taking a look at our IPv6 information. So I'm just going to go into the router on the left, and I'm going to do a quick show IP interface brief. And let's make sure that you guys have these configurations for your v4 network. All right, if you're reviewing these videos individually online, we built this network in a previous chapter, in a previous discussion. You can certainly pause the video and look at the topology and go ahead and create it yourself if you'd like. So you're still good with this configuration here, sir? Yes. Okay. You got the same configuration. All right. Now, in order for us to add IPv6, I want you guys to pay attention to the screen here. In order for us to add IPv6, we need to simply configure the interfaces, all of the interfaces, not just the Ethernet interfaces, also the serial link. Remember, this is a network, so it has to be configured as well. We're going to be configuring each of our interfaces. You guys have, after our subnetting discussion, you now should have a better understanding of what those numbers represent on the topology diagram. Those are not assignable addresses to any device. Those are actually the network IDs. You follow me? This is network 10.0. This is network 11.0. Well, guess what? This is network 2001 0db8 ACAD:1/64. /64 is 64 bits, isn't it? 2001 is 16 bits. 0db8 is 16 bits. ACAD is 16 bits. And 1 is 16 bits. So those are the network IDs. All of the router LAN interfaces. All of the router LAN interfaces are :1 in their respective subnets. Look at how we configure the address information on our interfaces. Now, you guys don't have to do the no shutdown because that was already done when you did your initial configuration. You guys don't have to do the IPv4 configuration because that was already done in your initial configuration. So essentially what we're doing is we're adding our IPv6 address. Be very careful when you're doing this configuration. Pay attention to the addresses that you're putting into the router, because when a router has IPv6 running, you can assign more than one address to the interface. You can assign more than one IPv6 address to an interface. So if you accidentally make a mistake on your IPv6 interface, you need to remove that address before you can add another one. Otherwise, you'll have multiple addresses. Also notice that you have to enable IPv6 on the router itself. We do that by using the IPv6 unicast-routing command in global configuration mode. So both routers will need this command. How many interfaces am I going to be configuring on the router on the left? How many interfaces? 3. And how many interfaces am I on the right? 3. Okay. The PCs also need to have IPv6 addresses. The PCs are going to be :10 in their respective subnets. So PC1 is going to be 2001:DB8:ACAD:1 :10. The PC on the right, PC3, 2001:DB8:ACAD:4 :10. All right? So I'm going to pause the recording here for a minute, and I'm going to give you guys a opportunity to start configuring these addresses, and then we'll go through it together as a group. Okay, so I'm going to go ahead and start my configuration. And if you're still doing your configuration, that's fine. You can still kind of follow along. But the first thing I'm going to do is IPv6 unicast routing to turn on my IPv6 stack. Routers don't have these on there by default. If I go into interface GI00, we're going to do IPv6 address 2001. Let's see what we got here. DB8 :ACAD:1 :1/64. And for interface GI0/0, 0/1, excuse me, we're going to use the same network essentially, just network number 2. So I just use my up arrow to switch to the command, the previous command in my history, and then I go ahead and just change that to a 2. For interface serial 0/0/0, we are going to use the 3 subnet. And for this link on the left, it is 1, based on the diagram. And we're done with that router. Now, let me go ahead and do the router on the right. Config T IPv6 unicast routing, interface GI00, GI is gigabit Ethernet, IPv6 address 2001:DB8:ACAD:, and for this router on the right, we're going to be using network 4 or subnetwork 4 and subnetwork 5, and for the serial link it's going to be 2. When I say subnetwork, I'm talking about these here. Remember, when you get the network from your service provider, what prefix are you most likely going to receive from your service provider? What prefix length? 48, right? Maybe something larger than that. It may not always be a /48. You might get a /56 or even something smaller, but we're subnetting that /48 using the additional 16 bits for each of our subnetwork IDs. So this is subnetwork 1, subnetwork 2, subnetwork 3, subnetwork 4, subnetwork 5. All right? So ACAD :4 :1/64. Notice that we do put the mask in as prefix notation. That's the only way that we do it in IPv6. This guy is going to be subnetwork 5. And for interface serial 000, it's going to be subnetwork 3 and host ID 2, because the other link is 1. All right? So let's just go through and verify, make sure everybody has the right information before I start showing you a few other things and we start doing some additional configurations. So I'm going to go ahead and get out of config mode. Everybody go into the left router, whatever that's called. In my case, it's called router 5, but I named it router 1. But go into the left router, show IPv6 interface brief. Remember, we are now working with IPv6. We're not working with IPv4. We have done something to this router called dual stack. These routers are actually running both protocol stacks. Okay? Okay, Cody, that's not a problem. I'll make a couple of other points here to help you get caught up while you're still working on it. All right. A couple things I want to point out about this particular output. First of all, we know what the show IP interface brief command did, right? It gave us a list of all the interfaces that we had on our platform. And sure enough, we see a list of all the interfaces that we have on our platform, right? So it's the same in that regard. The other thing that show IP interface brief showed us was the status and the protocol, right, of the physical layer and the data link layer status of our interface. You guys remember we had that discussion when we talked about the status column represents layer 1, the protocol column represents layer 2. Well, we have the same thing here, except for it's in these brackets. So the first up that you see there indicates the physical layer. The second up that you see there indicates the data link layer. Does that make sense?
Yes.
Are your addresses the same?
Yes, sir.
Great. 2001 DB8 ACAD1 :1 for gig 00. 2001 DB8 ACAD :2 :1 for gig 01. And 2001 DB8 ACAD :3 :1 for gig or serial 000. But you will also notice, and by the way, these addresses that we assigned, these are called global unicast addresses, meaning that they're routable. These are routable addresses. These are routable addresses. Don't they come from the routable space? 2000 :3. So they do come from the routable space. All right? But you'll also notice that there's a secondary address on the interface.
Is that the MAC address?
That is the link local address. It's called a link local address. Now, you guys just follow along on the screen here. I'm going to describe how that link local address was derived. Let's go ahead and copy that address. So I'm going to go into my notepad here and paste that. And then I'm going to do a quick show interface GI 00. And what I'm going to grab from show interface is the MAC address of the interface. So we'll go ahead and copy that. So that is the MAC address on the interface, and above that is the link local address that was assigned to the interface. Now, if you recall from our discussions in the IPv6 section, link local is derived, using FE80:10 followed by the EUI, can't type, 64 host address. So how did I derive the EUI 64 host address? You take the MAC address, 0030A3184801. You divide that MAC address in half. You drop in an FFFE. That's first step. Drop in the FFFE. Now we have a 64-bit address instead of a 48-bit address. Agreed? You guys follow me so far? And actually, we can start to see, here's 4801, here's 4801. Here's 81EF, here's 81EF. Here's FF3A, here's FF3A. I read it backwards for a reason, because there is one more step to this EUI 64 process. We have to invert the 7th bit. Well, the first 4 bits are 1, 2, 3, 4. That represents this 0 in the MAC address. The next 4 bits are 1, 2, 3, 4, which represents this 0 in the MAC address. I invert this bit, and this becomes 0, 2 in hex. 0, 2. All right. Now, if I was to write this as the link local address, I'll put it right under the link local address here. We know it starts with FE80, double colon. The 0 is not mandatory because leading zeros can be dropped off. This leading, or this A here corresponds with that A. And then we have the remainder of our address. So that is how we derived that link local address from the MAC address on the interface. Okay? Now there's a very important thing that I want to point out. Link local addresses are used all the time in all sorts of forms and fashions, right? They're used for neighbor discovery. They're used for router advertisements. They're used for next hop addresses for routes in the routing table and so on. So personally for me, I don't particularly care to see link local addresses like this in all my databases. Honestly, it's a little bit hard to read, and looking at those link local addresses can be difficult if you have lots and lots of interfaces. So in the router, we actually have a choice to set those link local addresses manually. This wasn't in the lesson, but since I do this in the real world, I feel compelled to kind of tell you. So what I do, and you guys don't have to do this, I'm just demonstrating this, config T, interface GI00, okay, IPv6 address, FE80, double colon. Now what I can choose to do here is I can say, okay, I want to make this one 1:1. All right, 1:1. Now why did I choose 1:1 in this case? Because that corresponds to the subnetwork and the host address of the router. You can make the link local addresses anything you want. All right, I've chosen to make it 1:1. The link local address, of course, has to be unique on the link, but it doesn't have to be unique across the entire network because by definition, it's an address that's only used on the wire. So the link local addresses that exist on these gigabit Ethernet interfaces will never be discovered by the router over here. It's almost like a MAC address. It doesn't go through a router. All right? Now you have to add link local at the end because you're specifying a link local address. Now Geo asked the question, why would I change it? Later on, you guys are going to see, when we do our OSPF and EIGRP, you're going to see that neighbor relationships. When you look at your neighbor table, in IPv6, those neighbor relationships are based on link local addresses. The next hop address in your routing tables is based on link local addresses. So if you're trying to troubleshoot the network, you're trying to identify what the next hop is or what the destination is or who the neighbor is, sometimes it's hard to recognize what that neighbor is if they have an EUI64 address because they're basically completely random. But if you have clean link local addresses, right? Interface GI01, we're going to go ahead and make this link local address subnetwork 2.1, interface serial 000. I'm going to make that link local address 3:1. Now if I do a show IPv6 interface brief, it's very clean, right? But you'll see later, when I have routing set up, the destination networks, the next hop addresses, the neighbor relationships, the databases, all reference the link local address. And if you have, like I said, a bunch of link local addresses that have EUI64 formats, it can be difficult to troubleshoot and identify where those addresses exist. It's not required. Link local addresses work perfectly by themselves. And of course, by setting them manually, you're running the risk of creating duplicate errors or some kind of issue. But if you use a naming scheme, or a numbering scheme, I should say, it would be very easy. All right? Clean is better, too. Clean is better. So we've got our network set up. I'm not going to change the link local addresses here, and you guys don't have to change the link local addresses either. I wanted to just demonstrate that that was a possibility if you're configuring an IPv6 network. So we've got our network set up. Now, how do we test it? Well, we saw a whole bunch of commands previously that we used to test IPv4. Show IP interface brief, show IP route, show run, show interface, show IP interface. Well, guess what? All of these commands exist in IPv6. The only difference is we replaced the word IP, or the argument IP, with IPv6. So we do show IPv6 interface brief, show IPv6 route, show IPv6 routers. That's a little bit of a different command. So this is what I was talking about that link local configuration. Those link local addresses were derived from the EUI64 process. Can you identify what interface or what network that belongs to based on that configuration? No. Right? All right. Now go ahead and save your file. We're going to be using this file, like I said, throughout the rest of today. We're going to be setting up RIP. We're going to be setting up static routes and so on. But we're done with the file for right now. You can minimize it or save it if you like. And we're going to get into some more lecture, and then we're going to wrap up this chapter, and then we're going to start getting into some other discussions about different types of routing as we move through the rest of today. As I already alluded to, routers choose what routes to put into their routing table based on something called a metric. The metric is a value used to measure distance to a particular destination. However, our routing protocols all choose how to get to that destination with different methods. The best path is going to be whichever path is measured with the lowest metric. These are the protocols that we're going to be talking about throughout the rest of today. RIP, the Routing Information Protocol, OSPF, Open Shortest Path First Protocol, the Enhanced Interior Gateway Routing Protocol, and the Border Gateway Routing Protocol. As you can see, every single one of these protocols has a different way of calculating the best path. RIP uses hop count. That is a horrible metric. What is a hop?
Going from one device to another.
Going through a router, right. As you move through the network, you pass traffic through routers. And each time you go through a router, that's considered a hop. Why is that a bad metric? Well, if I have a router here that wants to reach a network destination, and let's say that that network destination is down here, all right? So here's network X. Actually, I need to add one more router here. There we go. There's network X, and I'm running RIP on my router here. We'll call this R1. So R1 could choose to take this path, or R1 could choose to take that path. You guys agree? Okay. If the metric is hop count, which path is going to be chosen? The one with the least number of hops. So here we've got 1 hop, 2 hops. So the metric for that path is 2. Here we've got 1 hop, 2 hops, 3 hops. So the metric for that path is 3. So R1 is going to choose this top path. Okay, that sounds good. Seems logical. Let me clean this up real quick. What happens when the paths look like this? Same topology that we had before. Right? But now, this path is 1 kilobit per second, and this path is 1 terabit per second. That's right. RIP still uses that path because the metric is hop count. It has no concern for bandwidth at all. So that's not a very good metric. But you'll notice that OSPF, which is one of the most widely used routing protocols, bandwidth is a component. EIGRP, bandwidth is a component. So these two protocols are considered to be relatively intelligent, and they make good decisions about how to reach destinations. Now, BGP is a little bit different. BGP doesn't use a metric at all. It uses something called path attributes, and we'll see more about that later on. BGP is not a traditional routing protocol. So fundamentally, routing protocols make decisions on how to reach network destinations based on a metric. What happens if I have 2 paths that have the same metric, or even more than 2 paths with the same metric? When a router has 2 or more paths with the same metric, in most cases, the only exception is with BGP, but in most cases, the router is going to use both paths. All right? You should mention what the default EIGRP metric options are. Absolutely. When we get into the chapter for EIGRP, we will be talking about all of the defaults for those protocols. Trust me, we are going to get into a lot of detail about these protocols. Yes, sir?
Does that mean it's going to be sending that twice?
It means it's going to be using both links, and it's going to be load balancing, meaning that some data will go over one link, other data will go over the other link. You can identify that in a routing table. When you see a routing table entry with a single code but multiple entries, that indicates that there's load balancing occurring. In fact, I mentioned we would talk about what's in the brackets later on. The second number in this bracket is, in fact, the metric. So the metric for this path to get to the 1.4 address, I'm guessing that's maybe a loop back or something, I don't know. It's kind of a strange network entry, but to get to the, oh, it's a /31, that makes sense. To get to the 1.4 address, I can go two ways. I can go to 1.3 or I can go to 1.0. All right? Now you look at 1.0 and you say, well, that can't be an address. That's, you know, it's because we're using a /31 in this case. /31s kind of act differently than normal networks. Okay, that's not really the point here. The point is that we have two ways of reaching that destination. Notice that the number in the bracket is the same. 307.200, 307.200. Why aren't routers designed to dynamically add new devices to its table like switches? Because that would be very, very risky. The security vulnerabilities that would come into play if routers would simply just add themselves to a network and start exchanging information is pretty significant. Plus, how do you decide what protocol you're going to use by default? There are at least 5 mainstream routing protocols that exist. Who's to say which protocol you're using in your network? Right? Switches basically operate fundamentally the same no matter what the vendor is, no matter what the function is. They work at layer 2. They work with MAC addresses. They all have the same default VLAN configuration. Routers do not. Okay? Let's see. The external or the balance between security and the open flow of information. Absolutely. Now, I'm not going to suggest that the reason why routers don't have a configuration by default is purely for security reasons, but routers are far more complex than switches are. The configurations that you can apply to a router, significantly more complex. All right? As we will see throughout the rest of today. The other thing that I want to point out, and I think this is very important to understand, is how routers match routes in the routing table. It is unlikely, but it is perfectly possible that you could have multiple routes in the routing table that look similar. These are distinctly 3 different routes, right? Because the prefixes are different. One's a /12, one's a /18, one's a /26. Now, this is unlikely to occur in most networks, but let's say that it did. Oh, it just did, right? Now we have a router that has 3 similar routes. They're kind of overlapping. And we have a packet coming into the router with this IP address. Though this packet actually matches all 3 routes in the routing table. But the router will always choose what it considers to be the best match. And the best match is based on how many bits in the network ID match how many bits in the actual packet being routed. The highlighted portions of those addresses that you see there are, in fact, the network bits, aren't they? There's 12 network bits here, there's 18 network bits here, there's 26 network bits here. Because these 26 network bits match the first 26 bits of the packet, that is what we would consider the longest match. All right? That was what we consider the longest match. Are we going to go over route redistribution? No, we are not going to be going over route redistribution. That is covered very heavily in the CCNP course, which I hope I see you guys in that course in the future at some point. We do route manipulation, we do route redistribution, we do a much more in-depth discussion of BGP, as well as a whole bunch of other things in the CCNP class. All right. Our discussion of routing protocols in this class borders on what we cover in the CCNP anyway, because routing is one of my favorite topics to teach, so I tend to get a little bit more in-depth and involved in those protocols, generally at the detriment of covering other things like frame relay and PPP. But routing is extremely important, so we do spend quite a bit of time talking about it. Now, here's another concept that I want to talk to you guys about. It's called route summarization. Route summarization is a cornerstone of any good network design, especially when you're talking about enterprise-level network design. Consider that you have this topology here. You've got a router that is connected to maybe a branch office or whatnot, and in that branch office you've got a whole bunch of networks that exist. And then you've got a router up here connected to another branch office with a whole bunch of routes that exist behind that router. But the only way to get in and out of those branch offices is through the router, okay? Well, there is a concept in routing that's called route aggregation or route summarization, which allows us to advertise networks to other routers, but instead of advertising all of the networks, which would fill up my routing table and take up a lot of memory and processing power and whatnot, instead of advertising all the networks, I want to advertise a summary of those networks. Because think about it. If somebody's in this middle cloud here and they want to go to 4.0, they're going to go to that router. If they want to go to 5.0, they're going to go to that router. 8.0 to that router. 9.0 to that router. So why does that router have to advertise 4, 5, 8, 9, and 10? Why can't it simply advertise a summary of those routes? It's kind of like saying, I want to go to a bunch of places in Orange County. Tell me how to get to every single one of those places, but there's only one way to get to Orange County. So what are you going to tell the person first? You're going to tell them how to get to Orange County. Once they're in Orange County, they can rely on other people to tell them how to get to the individual locations. All right? So route summarization is this concept of taking essentially a bunch of subnets and advertising those subnets as a larger network. That's why it's called route aggregation. We're aggregating a bunch of smaller networks and making them look like one large network. Isn't this just the opposite of subnetting? Subnetting is taking a large network and representing it as a bunch of small networks. Well, route summarization is supernetting, taking a bunch of small networks and representing them as one large network. All right?
For the right down the right, where you represented 192.168.0/22. Wouldn't that also incorporate 192.168.11.0/24 in there?
Yes. That's right. So let's talk about, the question was, wouldn't the 8.0/22, wouldn't the 8.0/22 also include other networks? All right. Now, we haven't gone into the math yet, guys. I've just explained the concept, right? We're going to be looking at how these are calculated here in a second. In fact, let's go ahead and do that right now. So let's say that I have, I'll use a different example. 10.10.10.0, 10.10.11.0, and we'll start with those two. We'll start with a very basic, we want to summarize these two routes to our destination. Whoever we're advertising this network to, we want to summarize these two routes. Does everybody agree that the routes have this in common? Yes? So we know that our summary is going to include at least 10.10 because that's what's common to both of those networks. Now, if I look at the third octet, 00001010 equals 10, and 00011011 equals 11. You guys follow me? What are the common bits between both of those numbers? The first 7 bits. Those are common between both numbers, aren't they? So my summary would be the least common denominator, which is 10. And as far as the mask goes, it's whichever bits are common. So we have 8 bits here that are common, plus an additional 8 bits here that are common, plus an additional 7 bits here that are common. Which means essentially the last bit can be anything. It's almost like talking about wildcards. The last bit can be anything. Now, in this particular summary, it's perfect because it happens to include only those 2 subnets. However, if we look at our example, we've got 8, 9, and 10, all right? 192.168.8.0, 192.168.9.0, 192.168.10.0. Does everybody agree that 192.168 is common to all 3 of those networks? Yes? And 8 is equal to 00001000, 9 is 00001001, and 10 00001010. So what is common to all 3 of those octets? Only the first 6 bits are common. You see that? So these 2 bits are unique, these 2 bits are unique, these 2 bits are unique. Which means, and by the way, what's the least common denominator? When I say the least common denominator, you set the wildcard bits to 0. The value of that octet is the beginning of your summary range. In this case, it's 8, excuse me. And what is my subnet mask? In this case, my subnet mask would be 8 common bits plus an additional 8 common bits, that's 16, plus 17, 18, 19, 20, 21, 22. So that route represents those 3 networks. But it also represents a 4th network, doesn't it? Because if these 2 bits can be anything, that means that they can be this, which equals 11. 11 wasn't part of the list. See, the thing about summarization is because it's binary, we're working with binary numbers, you can only summarize in blocks. You can only summarize 1 network, which really isn't a summary. You can summarize 2 networks. You can summarize 4 networks. You can summarize 8 networks. You can summarize 16 networks. You can summarize 32 networks. But you cannot summarize 10 networks. You cannot summarize 5 networks because we're dealing with binary, powers of 2. So the people inside the cloud here would actually think, based on this route, that they can route to the 11 subnet, even though the 11 subnet doesn't exist in that cloud. You have to be careful with summarizations. If the 11 subnet was down here, we would have a problem. Maybe. Maybe. Because 11 is included in here as a /22, But what if this router was advertising 11 as a /24? Which route gets used? The /24, because it's more specific. It's still not clean. I would still not recommend it, but technically it would work because the routers in between, they're going to see this 22, they're going to see the 24, they're going to choose the 24. All right? The thing about doing summarization effectively, and when you're designing a network, these are kind of the things we were talking about yesterday. Where do I put my addresses? How do I know where to put my networks? When you're designing a network, you want to make sure that you have contiguous address space, meaning that the blocks of networks that you have, don't put the 4 here and the 5 here and the 8 here and the 9 here and the 10 here and the 11 here, because then you will not be able to summarize. You will not be able to take advantage of more efficient routing through the use of summarization. Now, if this network was the only network I had, these networks were the only networks I had, sending in, what is that, 1, 2, 3, 4, 5 routes as opposed to 2 routes, obviously that's a bit of a waste of time, isn't it? When we talk about summarization, we're talking about summarizing potentially hundreds of networks or thousands of networks. But summarization also assists us with convergence issues. Convergence is the concept that if something changes in the network, how long does it take for that change to be learned? How long does it take for that change to be propagated? The faster a network converges, the more efficient it is. If I'm sending in 8.0/22 into the cloud, and the 9 network goes down, does the cloud care? Does the summary change? No. The summary doesn't change. So the /22 route is still valid for the 8 network and the 10 network. Internally here, we would have to converge, but in the backbone, in the cloud, we would not have to converge because the summary is still valid. We can also summarize with IPv6. So we've got, here we go, 2001, what do we have? 410, and then we've got, what we call it, 2001, 410:5, 2001, 410:6. Now, these are all /48s. So you would write this as /48, /48, /48. You guys agree that that is 48 bits, right? Is that 48 bits? I abbreviated it, right? So technically it's 2001:0410:0004. But do you guys agree that that's 48 bits? How many bits exist in each hextet? 16. So we have 16 bits, 16 bits, 16 bits, that's 48. So these are network IDs. If I wanted to summarize these, guess what? It's exactly the same as IPv4. 2001:410 is common to each one of these networks. I convert 4 to binary. Now, keep in mind, when you're converting 4 to binary, make sure that you're using all the bits, right? 0000, 0000, 0000, 0100. How did I get from this to this? How did I get from the 4 to that? Well, 4 is hexadecimal. In addition, we have 16 bits. The leading zeros are not written down, but they're still there. All right? Yes, Ivan got it right. 0004 is actually what the value of the hextet is. So I'll just copy this. So now we have 5 and we have, 6. Get this right here in a second. All right. Well, pretty much messed that up. All right. So there's 5 and there's 6. You guys agree with that? Which bits are common? These bits are common. This bit, this bit, this bit. So the first 14 bits are common. We have 32 bits that we already knew were common, which is the 2001-0410, plus we have an additional 14 bits that are common in the third hextet. What is the value of this third hextet here, though? Well, the minimum, the least common denominator with these is 4, right? 4, and what would be my mask? 46, exactly. You don't have to be scared of IPv6 because ultimately it's the same as IPv4. Yeah, there are some differences in operations and whatnot, but from an addressing perspective, we're still using ones and zeros. So summarization is good stuff. I'm glad you feel smart. That's definitely important. Now, will you remember it when you wake up in the morning? All right. Okay. Today is one of those smart days. Today is no more OSI model, no more stuff that people see from time to time. This is the good stuff. This is the engineering stuff that we're going to be doing today. Okay? So you'll continue to feel smart today, hopefully. So fundamentally, that is summarization. Now this slide should make sense. You should understand how we derive those red values. You will have to do some summarization calculations, most likely on the second exam, not the first exam. We're really starting to move, even though this is still technically under CCENT, we're really starting to move pretty heavily into what we see on the second test as well. Okay? All right. Here is a pretty picture to describe everything that we just did in Notepad. So if you want to reference it a little bit later on, the red bits, of course, are the common bits. The black bits are the bits that are, well, we don't care about, right? Those are my host portions. All right.
For route summarization, this is something that the routers do it automatically.
No, they do not. The question was, do routers do summarization automatically? And the answer is no. Route summarization is something you have to configure manually. In OSPF, you can only summarize at specific boundaries. In EIGRP, you can summarize on any link, but summarization does not occur automatically. All right? I'm going to show you guys how to configure summarization. Now, here's another concept, very heavily covered on the exam, actually, concept of administrative distance. You don't typically run into this when you have a production network, because usually when you're running a production network, you're only running one protocol. But it is possible that you could see this in certain scenarios. Before I get into the discussion of the slide here, let me go ahead and just put in a diagram. Router here, router here. We're going to use the same topology I used before. Router here, router here, router there. Okay? Now I'm running both EIGRP and RIP. For some reason, whatever it is, maybe I'm in the process of converting. I bought a company and we're merging the networks and we decided to run both protocols for a time, whatever. In all of these routers, I'm running two routing protocols, RIP and EIGRP. Okay? How many routing tables does a router have? If I'm running RIP, EIGRP, OSPF, how many routing tables do I have? One. I only have one routing table. What goes into that routing table are my best routes, period. Okay? What goes into the routing table are my best routes. Well, here's the problem. If I have a network over here, we'll call this network A, since we have a bunch of X's in our routers. We'll call that network A. And obviously R1 needs to decide how to get to network A. We already determined that RIP is going to go ahead and choose that path. Okay? Then I'll put a little circle around my RIP here. RIP is going to choose that path because of its metric, hop count. And let's go ahead and say that the bottom path is faster, has better bandwidth. EIGRP is going to choose that path because its metric is primarily based on bandwidth. It's actually much more complex than that. There's 5 K values, and there's a formula, K1 times the bandwidth, 10 to the power of 8 divided by bandwidth in kilobits per second, divided, or times 256. And there's a whole formula that we use to calculate the metric. But the bottom line is bandwidth is a major component of that, okay? So R1 has to now decide, do I put the EIGRP route in the routing table, or do I put the RIP route in the routing table? Do I put the EIGRP route in the routing table, or do I put the RIP route in the routing table? The metric for RIP is completely incompatible with the metric for EIGRP. There's no way to compare hop count to bandwidth. But I still have to choose the best path. All right? Well, here's the scenario that we have. It's called administrative distance. All right? Let me close the door real quick. It's called administrative distance. All right? And what administrative distance defines is the trustworthiness of the routing information source. The lower the number, the more trusted the source. The lower the number, the more trusted the source. Well, take a look. It kind of makes sense. If it is a connected route, it has an administrative distance of 0. Connected interfaces should definitely be the most trusted interfaces because they're directly connected to the router. In our scenario, RIP has an administrative distance of 120. EIGRP has an administrative distance of 90. So guess which one goes into the routing table? The EIGRP route. The lower the administrative distance of a protocol, and by the way, these are numbers that Cisco assigns. Other vendors have different AD values. It's kind of comical, actually, because IGRP, which wasn't really a very good protocol, is rated above OSPF. But guess what? IGRP and EIGRP are both Cisco protocols. IGRP doesn't actually even exist anymore because it wasn't that good. All right? I want to also be clear that an administrative distance value is not a metric. The only time administrative distance comes into play is if you're learning about the same route, the exact same route, from 2 different sources. What is not the same route? 10.10.10.0/24 from EIGRP is not the same as 10.10.0.0/16 from RIP. Okay? When I say the exact same route from multiple sources, I mean literally the same route. Same prefix, same IP, everything. We've got a question online. How is the routing protocol determining the bandwidth? Actually doing tests or using the interface's bandwidth? Well, I'll answer that question, but only briefly, because when we get into the routing protocols, we'll talk about this. But the bandwidth values that routing protocols use are theoretical. They are theoretical values. Okay? They're not practical values. They are theoretical values. All right? Speed and duplex have no bearing. I will explain what that means in detail as we move on to our next lessons, but that's what it means. Okay, so what does the routing table contain? The routing table contains directly connected routes. Those directly connected routes are the routes that are physically attached to the router. Those will show up in the routing table as a C, and they'll have a corresponding L route, which is a local route, to describe the actual interface. But those are my connected routes. Remote routes could be one of two kinds, either static, which will show up as an S, or RIP, which will show up as an R, or OSPF with an O, EIGRP is a D, and so on. All right? What are remote routes fundamentally? Remote routes are the routes that the router is not physically connected to. And the only way a router can reach those remote routes is if it's told how to do so. In addition to identifying the routes, we also identify how we get to those destinations. That's called the next hop. Remember, the goal of a router is not to send the packet to the destination. It's to send the packet towards the destination through the next device. All right? Now, we can do things like static routes. Static routes are interesting because when you define static routes, you as an administrator is telling the router how to reach a destination. Look at the administrative distance of a static route. It's 1 by default. So Cisco said, hey, if you're putting in a static route, you must know what you're talking about. So even if I learn about the same route through EIGRP or OSPF, I'm going to use the static route because you told me to go there. The thing about a static route, though, is it's manually configured, which means it has to be manually changed if something changes in the topology. Now, they say here it benefits us by improved security and control of resources. Let's talk about the second part first, control of resources. Why do static routes have or require fewer resources? When I'm working with dynamic routes, what has to happen? Let's say we're all routers connected to the same network. What do we have to do to be able to learn routes? We have to talk to each other. We have to share information. See what I'm saying? Static routes, there are no advertisements. There are no neighbor relationships. There's no processing of incoming hello packets or updates or queries or replies or link state advertisements or link state requests or anything else that's required for dynamic routing to work. How about improved security? Well, when something is dynamic, like CDP, like VTP, like ether channel negotiation, like trunk negotiation with DTP, anything that's dynamic can be manipulated. If you don't implement it correctly, you can open yourself to vulnerabilities. Well, static routes don't do any negotiation. All right? Now, static routes are entered into the router in global configuration mode. Here is the syntax. I'm only going to mention one thing about this because we actually have a whole chapter for static routes coming up. But the number at the end here, I'm going to mention that because you'll probably see that on the exam. That number on the end represents the administrative distance. The default administrative distance of a static route is 1. What they've done here is they've changed it to 95. What would be the effect of that if I was running, say, EIGRP? What is the administrative distance of EIGRP? 90. So this static route would actually take a back seat to the same route learned through EIGRP. It's what we call a floating static route. We would have this in place if for some reason the OSPF or the EIGRP route would go away. Maybe the EIGRP process fails, maybe something gets misconfigured, whatever. All right? Are administrative distance hardwired within a router? No, they are completely configurable. They are set to values by default, but they are completely configurable. We don't do that in this class, but we do talk about manipulating administrative distances in the CCNP class. Should we memorize the administrative distances for the exam? You need to know the following administrative distances for the exam. Connected and static, EIGRP, internal, OSPF, and RIP. Basically the protocols that we're using. Basically the protocols that you're learning. All right? There's also another special type of static route. It's called a default static route. And a default static route is kind of like a gateway of last resort. It allows us to essentially ensure that the router will never drop a packet. Now, as far as the syntax goes, we don't have to worry about that. But what I will say is that if this particular router that I put this default route in doesn't have a route to a destination for a specific packet, it will send it to that address, 192.168.10.1. So routers with a default route will never drop a packet. Security configurations aside, if you have some policies to force the router to drop packets, but from a routing perspective, a router with a default route will never drop the packet. All right. Of course, we also have the option to do dynamic routing. Now, the benefit of dynamic routing is that the network is self-healing. If interfaces go down, if additional interfaces get added, the routes get re-advertised. If metrics change, the metrics get re-advertised. And the router can make decisions based on the actual picture of the topology. So this router over here is running EIGRP. This router is running EIGRP. These guys are exchanging information with each other saying, I have these routes, I have these routes, I can get to these destinations, these are the metrics, et cetera, et cetera. So it's almost like they're speaking a language. And they're sharing information in real time, dynamically. All right? A lot of benefits to that, but then also you have to understand the impact that that has on your topology. How much information is going to have to be exchanged? How do I secure that environment so somebody is not trying to inject false information into my environment? We have a question from Joe. So routers are not programmed to be added to new networks, but once programmed, share information about what is connected. In a nutshell, yes. By default, there is no routing protocol running. Routers don't do anything automatically. And whether or not they start sharing networks automatically depends on the scope of your configuration. You can limit the scope of that configuration to say, I don't want interfaces to be advertised automatically. Or you can do the opposite, okay? That will be become more clear as we start to get into our discussions of the routing protocol specifically. So in IPv4, we have basically 5 routing protocols. EIGRP, which used to be Cisco proprietary, it's now open to the public. Cisco still maintains control of it. OSPF, ISIS, yes, that protocol exists. It's a good protocol. A lot of service providers use this protocol. RIP version 1, RIP version 2, very bad protocols, very bad. And BGP. BGP is kind of on its own. The rest of those protocols have similar functions, but BGP is kind of its own little monster. In IPv6, we have similar protocols as well, all the same protocols, EIGRP for IPv6, OSPF version 3, ISIS, again, and RIP next generation, which is just as bad as the first generation. Okay? Believe it or not, RIP next generation uses the same metric, the same deterministic timers, the same limitations. Okay? And then we have multi-protocol BGP, which is basically BGP for address families and IPv6 and IPv4 and everything else. Okay? So that concludes our discussion or introduction to routing protocols. Of course, now we're going to start to do our deep dives into each of these protocols. But we'll go ahead and take our break this morning.